The year 1913 saw the publication of Henry Cavendish's Experiments of the Density of the Earth, a meticulous record detailing a groundbreaking endeavour to determine Earth's density and, consequently, the gravitational constant. While Cavendish performed his experiment in 1797–1798, its republication in 1913, edited by Arthur Stanley Eddington, serves as a poignant reminder of the enduring importance of Cavendish's work and its continued relevance to our understanding of fundamental physics. This essay will delve into the historical context surrounding Cavendish's experiment, the intricacies of his methodology, the significance of his results, and the lasting impact of his work on the scientific community. Cavendish's experiment did not emerge from a vacuum. It represents the culmination of a scientific quest to understand gravity, initiated by Isaac Newton's formulation of the law of universal gravitation. Newton's law, published in 1687 in Principia Mathematica, described the gravitational force between two objects as directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. However, Newton's law included a constant of proportionality, now known as the gravitational constant, often symbolized as g. Determining the value of g proved challenging, as it required measuring the gravitational force between objects of known mass. This is an exceedingly difficult task, given the weakness of gravity compared to other fundamental forces. Prior to Cavendish's effort, various attempts were made to estimate Earth's density, providing indirect routes to estimating the gravitational constant. One notable attempt involved observing the deflection of a plumb line near a mountain. By measuring the small angle of deflection caused by the mountain's gravitational attraction, one could estimate the mountain's mass and, thereby, Earth's density. However, these methods suffered from several limitations, including uncertainties in the mountain's mass distribution and the difficulty of accurately measuring small angles. Henry Cavendish, building upon the work of his predecessor John Mitchell, devised a far more precise and controlled experiment. Mitchell designed a torsion balance apparatus specifically for this purpose, but he died before he could conduct the experiment. Cavendish inherited the apparatus, modifying and improving upon it to achieve unprecedented accuracy. The torsion balance consisted of a lightweight horizontal rod suspended by a thin wire. Two small lead spheres were attached to the ends of the rod. Cavendish then brought two much larger lead spheres close to the smaller ones, attracting them gravitationally. This gravitational attraction caused the rod to twist, exerting a torque on the suspension wire. Crucially, Cavendish knew the torsional constant of the wire, meaning he knew how much force was required to twist the wire by a specific amount. By measuring the angle of twist caused by the gravitational attraction between the spheres, he could determine the force of gravity between them. Knowing the force, the masses of the spheres, and the distance separating them, he could then solve for the gravitational constant, g, using Newton's law of universal gravitation. The equation he effectively solved, though perhaps implicitly, can be expressed as force equals g times mass 1 times mass 2, all divided by radius. To minimize extraneous sources of error, Cavendish constructed the apparatus within a closed room. This setup mitigated the effect of air currents and temperature fluctuations, which could have interfered with the delicate measurements. He observed the apparatus from outside the room, using telescopes and precise measuring scales to determine the angle of twist without disturbing the experiment. This meticulous approach reflects Cavendish's dedication to scientific rigor. Cavendish's experiment yielded a value for the Earth's density of 5.448 grams per cubic centimetre. This result, while slightly different from the currently accepted value of 5.515 grams per cubic centimetre, was remarkably accurate for its time and represented a significant improvement over previous estimates. From Earth's density, Cavendish also calculated a value for the gravitational constant, effectively weighing the Earth. Though Cavendish himself focused on determining Earth's density, his experiment directly paved the way for a precise measurement of g, a fundamental constant that underpins our understanding of gravity. The value for g, that can be derived from Cavendish's measurement of Earth density, represents the first experimental determination of this key constant. The publication of Cavendish's experimental results in 1798 was met with considerable interest and acclaim. Within the scientific community, his experiment was recognized as a triumph of precision measurement and a testament to the power of experimental physics. However, a peculiar historical detail arises. Cavendish himself never explicitly calculated or stated a value for g. He presented his results in terms of Earth's density, a quantity that was of greater geological interest at the time. It was later scientists who extracted a value for g from Cavendish's data, highlighting the lasting legacy of his work. The 1913 republication of Cavendish's experiments, edited by Eddington, solidified Cavendish's reputation as a scientific pioneer. Eddington, a prominent astrophysicist known for his work on relativity and stellar structure, recognised the historical significance of Cavendish's experiment and ensured its accessibility to future generations of scientists. Eddington's editing likely provided additional context and commentary, further enhancing the value of the republication. Cavendish's experiment profoundly influenced subsequent research in gravitation and fundamental physics. His torsion balance technique became a cornerstone of experimental physics, used in a wide range of experiments to measure small forces and torques. The Cavendish balance, in modified forms, served instruments to measure the gravitational constant with ever-improving precision. The experiment served an early inspiration to physicists of the 19th and 20th centuries. Over the years, numerous scientists have refined Cavendish's experiment, improving the accuracy of the measurement of G. These refinements have involved using more sophisticated materials for the suspension wire, implementing feedback control systems to stabilize the apparatus, and carefully accounting for various sources of systematic error. Despite these improvements, the fundamental principle of the experiment remains the same, demonstrating the enduring elegance and ingenuity of Cavendish's original and the precise determination of the gravitational constant has far-reaching implications for our understanding of the universe. G enters into numerous equations in physics and astronomy, including those describing the motion of planets, the structure of stars, and the expansion of the universe. An accurate value for G is essential for testing the validity of gravitational theories and for making precise predictions about cosmological phenomena. For example, G appears in the equation relating the mass of a black hole to the radius of its event horizon. Uncertainty in G translates into uncertainty in our understanding of these extreme astrophysical objects. Moreover, Cavendish's experiment laid the groundwork for future experiments probing the nature of gravity. His work inspired scientists to search for deviations from Newton's law of gravitation at short distances, exploring the possibility of new fundamental forces or extra dimensions. The experiment represented the starting point for many inquiries. Modern experiments continue to refine gravitational measurements and explore the boundaries of our knowledge. It is perhaps an irony that Cavendish, a man of extreme reclusiveness and eccentric habits, should be remembered for an experiment that profoundly influenced our understanding of the universe. Cavendish possessed a brilliant intellect and a meticulous approach to experimentation, but he shunned publicity and preferred to work in isolation. His contributions to science were often understated, and he rarely sought recognition for his achievements. He meticulously recorded his findings, yet possessed a reluctance to publish. Cavendish's shyness bordered on the pathological. Stories circulated of him communicating with his female servants solely through written notes, avoiding direct interaction. He amassed a vast fortune through inheritance, yet lived a relatively simple life, devoting his wealth to scientific pursuits. This eccentric personality only adds to the mystique surrounding his groundbreaking experiment. The 1913 republication of Experiments of the Density of the Earth serves as a valuable historical document, providing insights into the scientific methods and intellectual climate of the late 18th century. It also stands as a reminder of the importance of preserving and disseminating scientific knowledge for future generations. Eddington's editorial work highlights the ongoing process of interpreting and re-evaluating scientific discoveries in light of new evidence and theoretical frameworks. In conclusion, Henry Cavendish's experiment to determine the density of the Earth represents a pivotal moment in the history of physics. His meticulous experimental design, his dedication to precision measurement, and his groundbreaking results laid the foundation for our modern understanding of gravity and the gravitational constant. The 1913 republication of his work, edited by Arthur Stanley Eddington, ensured its continued availability and accessibility to scientists worldwide, solidifying Cavendish's legacy as one of the greatest experimental physicists of all time. His work continues to inspire scientists to push the boundaries of knowledge and to explore the fundamental laws governing the universe. The sheer elegance and lasting impact of this experiment stands as a testament to human curiosity and ingenuity.